Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. In the field of cosmology and astrophysics, researchers and scientists sometimes refer to certain aspects of the universe as mysteries. And when they use this term, they are generally describing phenomena that have been observed and measured, but are not yet fully explained by current theoretical models. Or they are describing components of the universe whose exact nature remains under investigation through ongoing research and data collection. The word mystery, in this context, does not imply something unknowable or supernatural, but rather it refers to areas where scientific understanding is still developing, where measurements have been made, but the underlying mechanisms are still being studied, and where theoretical frameworks are being refined through careful observation and mathematical modeling. Scientists use this term in a very specific and technical way, meaning simply that there are questions which have not yet been answered completely, observations that do not yet fit perfectly into existing models, and phenomena that require further study before they can be described with full confidence and precision. When scientists speak about mysteries of the universe, they are often referring to observable phenomena that have measurable effects, but whose fundamental nature is not yet understood in complete detail. And this includes things like dark matter, which can be detected through its gravitational effects, but has not been directly observed as particles, or dark energy, which appears to be causing the expansion of the universe to accelerate, but whose properties are not yet fully characterized. These are mysteries in the sense that they represent gaps in current knowledge, areas where scientists are actively working to gather more data, develop better instruments, and refine theoretical predictions. The scientific approach to these mysteries involves careful measurement, repeated observation, peer review of findings, and the gradual accumulation of evidence that either supports or contradicts various hypotheses. And this process is slow, methodical, and based entirely on empirical evidence rather than speculation or assumption. The universe, as scientists understand it, refers to everything that exists within the framework of space and time, including all matter, all energy, all physical forces, and all the structures that have formed over the course of cosmic history. And when researchers talk about the universe, they are usually referring specifically to the observable universe. which is the portion of the total universe from which light and other signals have had time to reach Earth. Since the beginning of the expansion that is commonly called the Big Bang, the observable universe is defined by the limits of observation rather than by any actual edge or boundary, and it represents the region of space that can potentially be studied using telescopes, detectors, and other scientific instruments. Beyond the observable universe, there may be regions of space that exist but cannot be observed, because light from those regions has not yet had time to travel to Earth, or because the expansion of space has carried those regions beyond the range where their light can reach us. And scientists make this distinction very carefully when discussing what can and cannot be known about the total extent of the universe. The observable universe extends approximately 46 billion light-years in all directions from Earth, which is a distance that accounts for the expansion of space during the time that light has been traveling toward us. And this creates a spherical region centered on Earth. That represents the limit of what can potentially be observed using electromagnetic radiation or other signals. This boundary is not a physical edge, but rather a horizon beyond which information cannot currently reach us. And it is important to understand that this horizon is constantly expanding as time passes, and as light from more distant regions has the opportunity to reach Earth. The size of the observable universe is calculated based on the age of the universe, the speed of light, and the rate at which space has been expanding. And these calculations involve careful measurements of cosmic distances, redshifts of distant galaxies, and the properties of the cosmic microwave background radiation. Within the observable universe, scientists have identified and cataloged billions of galaxies, each containing billions or trillions of stars, along with vast amounts of gas, dust, and other forms of matter. And these structures are distributed across space in patterns that reveal information about the history and evolution of the universe. The distribution of galaxies is not random, but shows large-scale structure, with galaxies grouped into clusters, clusters grouped into superclusters, and vast empty regions called voids separating these concentrations of matter. And this structure formed gradually over billions of years through the action of gravity pulling matter together into increasingly dense configurations. The process of structure formation began with very small variations in density present in the early universe. And these variations were amplified over time as regions of slightly higher density attracted more matter, while regions of lower density became increasingly empty. And this process continues even today, as galaxies move through space under the influence of gravitational forces. Scientists study the universe using various methods and instruments, including optical telescopes that detect visible light, radio telescopes that detect radio waves emitted by cosmic sources. Space-based observatories that can detect X-rays and gamma rays that do not penetrate Earth's atmosphere, and specialized detectors designed to measure gravitational waves, neutrinos, and other signals that carry information about distant cosmic events. Each of these methods provides different types of information about the universe. And by combining observations made at different wavelengths and using different techniques, scientists can build up a more complete understanding of cosmic phenomena. The instruments used in astronomy and cosmology have become increasingly sophisticated over time, allowing researchers to observe fainter objects, measure distances more accurately, and detect signals from progressively earlier times in cosmic history. And this ongoing improvement in observational capabilities continues to reveal new details about the structure and evolution of the universe. One of the central challenges in cosmology is that direct observation is limited by the speed of light and by the transparency of the universe to different types of radiation, which means that some regions of space cannot be observed directly, and some phenomena can only be inferred from their effects on observable matter and radiation. For example, scientists cannot directly see inside black holes because no light or other signal can escape from within the event horizon, and they cannot observe the universe as it existed during the first few 100,000 years after the Big Bang, because the universe was opaque to electromagnetic radiation during that period. These limitations mean that scientists must rely on indirect methods, theoretical models, and careful interpretation of available data to understand phenomena that cannot be observed directly. And this introduces a degree of uncertainty into cosmological research that is acknowledged openly by the scientific community. The concept of dark matter is one area where scientists have observed effects that require explanation, but have not yet directly detected the substance responsible for those effects. And dark matter is inferred to exist based on its gravitational influence on visible matter and radiation. Observations of galaxies show that stars in the outer regions of galaxies move faster than would be expected, based on the amount of visible matter present. And this discrepancy suggests that there is additional matter present that does not emit or absorb light, but does exert gravitational force. Similar evidence comes from the motion of galaxies within clusters, the bending of light by gravitational lensing, and the patterns observed in the cosmic microwave background radiation. And all of these observations point to the existence of some form of matter that interacts primarily through gravity and makes up a significant fraction of the total matter in the universe. Scientists estimate that dark matter makes up approximately 27% of the total energy content of the universe, while ordinary matter, the kind that makes up stars, planets, and everything visible, accounts for only about 5%. And this means that the majority of matter in the universe is in a form that has not been directly detected in laboratories or through telescopes. Various candidates have been proposed for what dark matter might be, including weakly interacting massive particles, axions, sterile neutrinos, and other hypothetical particles that would have the properties needed to explain the observations. And numerous experiments have been conducted to try to detect these particles directly. But so far, no conclusive detection has been made. The search for dark matter continues using a variety of experimental approaches, including underground detectors designed to measure the rare interactions of dark matter particles with ordinary matter, particle accelerators that might produce dark matter particles in high-energy collisions, and space-based telescopes that look for signals that might be produced when dark matter particles annihilate or decay. The evidence for dark matter comes from multiple, independent observations that all point to the same conclusion. And this convergence of evidence from different sources is what gives scientists confidence that dark matter exists, even though it has not been detected directly. For example, when scientists study the rotation curves of galaxies, measuring how fast stars orbit around the galactic center at different distances, they find that the orbital speeds remain high even at large distances from the center. Whereas if only visible matter were present, the orbital speeds should decrease with distance. This pattern has been observed in many different galaxies and is consistent with the presence of an extended halo of dark matter surrounding each galaxy. And this dark matter halo provides the additional gravitational force needed to keep stars moving at the observed speeds. Similarly, when scientists study clusters of galaxies, they can measure the total mass of the cluster by observing how individual galaxies move within the cluster, how hot gas is distributed within the cluster, and how light from background galaxies is bent as it passes through the cluster. And all of these methods indicate that the total mass is much greater than the mass of visible matter alone. The gravitational lensing effect, where the path of light is bent by the gravitational field of massive objects, provides another way to measure the distribution of matter in the universe, including dark matter. And this technique relies on Einstein's theory of general relativity, which predicts that massive objects curve the fabric of spacetime, and that light follows these curves as it travels through space. By measuring how light from distant galaxies is distorted as it passes through foreground clusters of galaxies, scientists can create maps of the total matter distribution in those clusters, including both visible and dark matter. And these maps show that dark matter is distributed in clumps and filaments that extend far beyond the visible galaxies. The patterns observed in gravitational lensing are consistent with predictions from computer simulations of structure formation that include dark matter. And this agreement between observation and theory provides additional support for the dark matter hypothesis. The cosmic microwave background radiation, which is the oldest light in the universe, and was emitted when the universe was approximately 380,000 years old, also provides evidence for dark matter. Through the detailed pattern of temperature fluctuations observed across the sky. These fluctuations reflect density variations present in the early universe. And the precise characteristics of these fluctuations depend on the relative amounts of ordinary matter, dark matter, and dark energy present at that time. By measuring the size and amplitude of these fluctuations very accurately, scientists can determine the composition of the universe with considerable precision. And these measurements consistently indicate that dark matter makes up approximately 27% of the total energy budget of the universe. The measurements of the cosmic microwave background are among the most precise observations in all of cosmology and provide strong constraints on theoretical models of the universe. In addition to dark matter, scientists have identified another component of the universe called dark energy, which appears to be causing the expansion of space to accelerate, rather than slowing down, as would be expected from the attractive force of gravity. The evidence for dark energy comes primarily from observations of distant supernovae, which are exploding stars that can be used as standard candles to measure cosmic distances, and from measurements of the cosmic microwave background and the large-scale distribution of galaxies. These observations indicate that the expansion of the universe began to accelerate approximately 5 to 6 billion years ago. And this acceleration requires some form of energy that exerts a repulsive effect on cosmic scales, counteracting the attractive force of gravity. Dark energy is estimated to make up approximately 68% of the total energy content of the universe, making it the dominant component by far. And yet, its nature remains one of the most significant open questions in cosmology and theoretical physics. The simplest explanation for dark energy is that it represents the energy of empty space itself, a concept called vacuum energy or the cosmological constant, which was first proposed by Einstein and later abandoned but has been revived in light of modern observations. According to quantum field theory, even empty space should contain energy due to quantum fluctuations, and this vacuum energy would have properties consistent with what is observed as dark energy, exerting a constant pressure that causes space to expand at an accelerating rate. However, calculations of the expected value of vacuum energy based on particle physics, predict a value that is vastly larger than what is observed, a discrepancy of many orders of magnitude. That represents one of the most significant problems in theoretical physics. Alternative explanations for dark energy include the possibility that it is a dynamic field that varies in space and time, sometimes called quintessence, or that it represents a modification of general relativity on cosmological scales, meaning that gravity behaves differently on very large scales than it does in the solar system or within galaxies. Each of these possibilities has different implications for the future evolution of the universe and for the fundamental laws of physics. And scientists are working to design observations and experiments that can distinguish between these alternatives. The study of dark energy involves measuring the expansion history of the universe in great detail, mapping the distribution of matter on large scales, and looking for any deviations from the predictions of standard cosmological models that include a cosmological constant. The expansion of the universe itself is one of the most fundamental observations in cosmology and has been confirmed by numerous independent measurements over the past century. The expansion was first discovered through observations showing that light from distant galaxies is shifted toward longer wavelengths, an effect called redshift, and that this redshift increases systematically with the distance of the galaxy. This pattern is exactly what would be expected if space itself is expanding, causing the wavelength of light to stretch as it travels through expanding space. And this interpretation has been confirmed through many subsequent observations and is now a cornerstone of the standard cosmological model known as the lambda-CDM model, where lambda represents the cosmological constant associated with dark energy, and CDM stands for cold dark matter. The expansion of the universe does not mean that galaxies are moving through space away from each other, but rather that space itself is expanding, carrying galaxies along with it. And this distinction is important for understanding the large-scale dynamics of the universe. On smaller scales, such as within galaxies or within galaxy clusters, gravitational forces are strong enough to overcome the expansion and keep structures bound together. But on larger scales, the expansion dominates and causes the average distance between galaxy clusters to increase over time. The rate of expansion is characterized by a quantity called the Hubble constant, which describes how fast the expansion is occurring at the present time. And measuring this constant accurately has been a major goal of observational cosmology for decades. Recent measurements have yielded values for the Hubble constant that are somewhat inconsistent depending on the method used, with measurements based on observations of the early universe giving slightly different results, then measurements based on observations of the nearby universe. And this discrepancy, sometimes called the Hubble tension, is an area of active research and debate within the cosmology community. The history of cosmic expansion can be traced back to a time approximately 13.8 billion years ago, when the universe was in an extremely hot and dense state. And from that initial state, space has been expanding and cooling ever since, allowing matter and energy to form the structures that are observed today. The early moments of cosmic history are described by the Big Bang model, which is not an explosion in space, but rather the expansion of space itself from an initial, highly compressed state. And this model has been confirmed by multiple lines of evidence, including the cosmic microwave background radiation, the observed abundances of light elements produced in the early universe, and the large-scale structure of the universe. The Big Bang model does not address what caused the initial expansion or what existed before it, as these questions involve physics at energy scales far beyond current experimental capabilities. And scientists generally focus on describing what happened after the initial expansion began, rather than speculating about the ultimate origin. The cosmic microwave background radiation provides a snapshot of the universe as it appeared approximately 380,000 years after the Big Bang. At the moment when the universe cooled enough for neutral atoms to form, and for light to travel freely through space without being scattered by free electrons. Before this time, the universe was filled with a hot plasma of protons, electrons, and photons that were in thermal equilibrium. And this plasma was opaque to light because photons were constantly being scattered by free electrons. As the universe expanded and cooled, the plasma eventually became dilute and cool enough for protons and electrons to combine into neutral hydrogen atoms. And at this moment, called recombination, the photons were released and began traveling through space unimpeded. These photons have been traveling through the universe ever since. And as space has expanded, their wavelengths have been stretched from visible and infrared light into the microwave portion of the electromagnetic spectrum, which is why this radiation is now called the cosmic microwave background. The cosmic microwave background radiation is remarkably uniform across the sky, with a temperature of approximately 2.7 Kelvin, meaning that it corresponds to the radiation emitted by an object at about -270 degrees Celsius. And this uniformity reflects the fact that the universe was very smooth and homogeneous at early times. However, when measured very precisely, the cosmic microwave background shows small variations in temperature of about 1 part in 100,000. And these variations correspond to regions that were slightly denser or less dense than average at the time of recombination. These density variations were the seeds of all the structure that formed later in cosmic history. As regions of slightly higher density attracted more matter through gravitational attraction, and eventually collapsed to form galaxies, stars, and other structures. The detailed pattern of temperature fluctuations in the cosmic microwave background encodes enormous amounts of information about the properties of the universe, including its age, composition, geometry, and the processes that occurred in the early universe. And measuring these fluctuations has been a major focus of observational cosmology for several decades. The large-scale structure of the universe refers to the distribution of matter on scales ranging from tens of millions to billions of light years. And this structure includes individual galaxies, groups and clusters of galaxies, superclusters, filaments, walls, and voids. Galaxies are not distributed randomly through space, but instead are organized into a cosmic web with dense filaments and sheets of galaxies surrounding large empty regions called voids. And this pattern emerged naturally from the action of gravity, amplifying small initial density fluctuations over billions of years. The formation of this large-scale structure began with the small density variations present in the early universe, which were imprinted at very early times, possibly during a period of extremely rapid expansion called inflation that may have occurred in the first fraction of a second after the Big Bang. These initial fluctuations were amplified by gravity as denser regions attracted more matter and became progressively denser, while less dense regions lost matter and became progressively emptier. Computer simulations of structure formation, which solve the equations of gravity and fluid dynamics for billions of particles representing dark matter and ordinary matter, have been remarkably successful in reproducing the observed large-scale structure of the universe. These simulations start with initial conditions based on the measured properties of the cosmic microwave background and evolve the distribution of matter forward in time, showing how small initial fluctuations grow into the complex web of structure observed today. The agreement between these simulations and observations of the actual distribution of galaxies provides strong support for the current understanding of how structure forms and for the role of dark matter in this process. Dark matter, because it interacts only through gravity and not through electromagnetic forces, can collapse into dense structures more efficiently than ordinary matter. And the dark matter halos that form through this process provide the gravitational scaffolding that allows ordinary matter to collect and form galaxies. Galaxies themselves are enormous collections of stars, gas, dust, and dark matter, bound together by gravity, and they come in a variety of shapes and sizes, including spiral galaxies with rotating disks and spiral arms, elliptical galaxies with smooth, featureless appearances, and irregular galaxies with no clear structure. The Milky Way, the galaxy that contains the solar system, is a spiral galaxy with a diameter of approximately 100,000 light-years and contains several hundred billion stars, along with vast quantities of gas, dust, and dark matter. Galaxies form through the gradual accumulation of matter in regions that were slightly denser than average in the early universe. And this process continues over billions of years. As galaxies grow by accreting gas from their surroundings and by merging with other galaxies, the formation and evolution of galaxies is a complex process that involves gravity, gas dynamics, star formation, supernova explosions, radiation from stars and black holes, and many other physical processes. And understanding galaxy formation in detail is an active area of research in astrophysics. The formation of galaxies began relatively early in cosmic history, with the first small galaxies forming within a few 100 million years after the Big Bang. And these early galaxies were much smaller and less massive than typical galaxies observed today. Over time, these small galaxies merged together to form larger galaxies, and gas flowing into galaxies from the intergalactic medium fueled the formation of new stars, gradually building up the mass and structure of galaxies. The rate of star formation in the universe as a whole has varied over cosmic history, with a peak occurring approximately 10 to 11 billion years ago, when the universe was about 3 billion years old, and declining since then, as the supply of available gas has been depleted, and as the expansion of the universe has made it more difficult for gas to fall into galaxies. Observations of distant galaxies, whose light has been traveling for billions of years to reach Earth, allow astronomers to study galaxies as they appeared at different times in cosmic history, and to trace the evolution of galaxy properties over time. Stars form within galaxies when clouds of gas and dust become dense enough that gravity causes them to collapse. And as the material collapses, it heats up and eventually reaches temperatures and densities high enough for nuclear fusion to begin in the core. The process of star formation converts hydrogen gas into stars, and each generation of stars produces heavier elements, through nuclear fusion in their cores, and through supernova explosions at the end of their lives. And these heavier elements are then incorporated into subsequent generations of stars and planets. The very first stars in the universe formed from gas that contained only hydrogen, helium, and trace amounts of lithium, which were the only elements produced in the Big Bang. And these first stars, sometimes called population 3 stars, were probably very massive and short-lived, ending their lives in powerful supernova explosions that enriched the surrounding gas with heavier elements. No population 3 stars have been observed directly, as they all died long ago, but their existence is inferred from theoretical models and from the chemical composition of later generations of stars. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. And they form when massive stars collapse at the end of their lives, or when matter is compressed by other processes into an extremely small volume. The existence of black holes was predicted by Einstein's theory of general relativity, which describes gravity as the curvature of spacetime caused by the presence of matter and energy. And under extreme conditions, this curvature can become so steep that it effectively traps everything within a certain region. Black holes have been detected indirectly through their gravitational effects on nearby matter, through the emission of X-rays from hot gas falling into black holes, and more recently, through the detection of gravitational waves produced when black holes merge with each other. The first direct image of a black hole's event horizon was obtained in 2019 using a global network of radio telescopes, showing the shadow of the supermassive black hole at the center of the galaxy M87. Black holes come in different sizes, with stellar mass black holes containing a few to a few tens of times the mass of the Sun, forming from the collapse of individual massive stars, and supermassive black holes containing millions to billions of solar masses, residing at the centers of most large galaxies, including the Milky Way. The formation of supermassive black holes is not fully understood, and several mechanisms have been proposed, including the growth of stellar mass black holes through accretion of matter, and through mergers with other black holes. The direct collapse of massive gas clouds in the early universe, and the formation of black holes from dense star clusters. Observations indicate that supermassive black holes were present when the universe was less than 1 billion years old, which suggests that they must have formed and grown very rapidly in the early universe. And understanding this rapid growth is an active area of research. The environment around a black hole can be extremely dynamic, with gas and matter spiraling inward and forming an accretion disk. And as this matter falls toward the black hole, it heats up due to friction and gravitational compression, reaching temperatures of millions or even billions of degrees, and emitting intense radiation across the electromagnetic spectrum. In some cases, black holes also produce powerful jets of particles and radiation that are launched perpendicular to the accretion disk and extend for thousands or even millions of light years into space. And these jets are powered by the rotational energy of the black hole and the magnetic fields threading through the accretion disk. The processes that produce these jets are not completely understood, but they involve complex interactions between matter, magnetic fields, and the curved spacetime near the black hole. And studying these processes requires both observational data and sophisticated theoretical modeling. Time and space are fundamental concepts in physics and are understood through the framework of relativity, which describes how measurements of time and space depend on the motion and gravitational environment of the observer. In special relativity, which applies in the absence of gravity, time and space are interwoven into a four-dimensional structure called spacetime, and different observers moving relative to each other will measure different values for time intervals and spatial distances, even though they are describing the same physical events. This relativity of simultaneity means that there is no absolute notion of what events are happening at the same time, and the rate at which time passes depends on the motion of the observer, with moving clocks running slower relative to stationary clocks, an effect called time dilation that has been confirmed by many experiments. General relativity extends these ideas to include gravity, describing gravity not as a force, but as the curvature of spacetime caused by the presence of matter and energy, and objects moving through curved spacetime follow paths called geodesics that represent the straightest possible paths in the curved geometry. This framework makes specific predictions about phenomena such as the bending of light by gravity, the precession of planetary orbits, the slowing of time in strong gravitational fields, and the existence of gravitational waves. And all of these predictions have been confirmed by observations. The concept of spacetime curvature provides a geometrical understanding of gravity that is fundamentally different from Newton's description of gravity as a force acting at a distance. And general relativity has been tested extensively in a wide range of circumstances, from the weak gravitational fields present in the solar system to the extreme conditions near neutron stars and black holes. The universe, on large scales, appears to be remarkably uniform and isotropic, meaning that its properties are similar in all directions and at all locations when averaged over sufficiently large scales. And this uniformity is reflected in the smoothness of the cosmic microwave background and in the statistical properties of the distribution of galaxies. This uniformity is somewhat surprising, given that different regions of the universe that are now widely separated were never in causal contact in the past, meaning that light or other signals have not had time to travel between them. And yet, these regions have very similar properties. The inflationary model, which proposes that the universe underwent a period of extremely rapid expansion in the first fraction of a second after the Big Bang, provides an explanation for this uniformity by suggesting that the entire observable universe expanded from a tiny region that was small enough to have been in causal contact, and therefore able to reach a uniform state before inflation began. The consistency and orderliness of the universe can be described mathematically through the laws of physics, which appear to be the same everywhere in the universe and at all times for which observations are available. These laws include the conservation of energy and momentum, the equations of general relativity that describe gravity, the equations of quantum mechanics that describe the behavior of particles and fields, and the standard model of particle physics that describes the fundamental particles and their interactions. The fact that these laws can be expressed as mathematical equations, and that they make predictions that can be tested through observation, is the foundation of the scientific method. And the remarkable success of this approach in describing natural phenomena is one of the most significant achievements of human intellectual endeavor. Mathematics plays a central role in understanding cosmic behavior because it provides a precise language for describing patterns, relationships, and predictions. And because the laws of physics can be expressed as mathematical equations that relate different physical quantities to each other. For example, Einstein's field equations of general relativity are a set of differential equations that relate the curvature of spacetime to the distribution of matter and energy, and solving these equations for different configurations of matter, allows physicists to predict phenomena such as the expansion of the universe, the formation of black holes, and the propagation of gravitational waves. Similarly, the equations of quantum field theory describe how particles interact and can be used to calculate the probabilities of different outcomes in particle collisions. And these calculations can be compared with measurements from particle accelerators. To test the theory, the role of mathematics in physics is not merely descriptive, but also predictive, meaning that mathematical models can be used to make predictions about phenomena that have not yet been observed. And these predictions can then be tested through new observations or experiments. This interplay between theory and observation is essential to the progress of science and has led to many discoveries, such as the prediction of the existence of Neptune based on irregularities in the orbit of Uranus, the prediction of the cosmic microwave background radiation before it was observed, and the prediction of the Higgs boson before it was detected at the Large Hadron Collider. The success of mathematical physics in making such predictions provides strong evidence that the mathematical descriptions capture something fundamental about the nature of reality. Although the question of why mathematics is so effective in describing the physical world remains a topic of philosophical discussion, some cosmic processes and phenomena are not yet fully understood, and this incomplete understanding reflects the current limitations of theoretical models, observational data, and computational capabilities, rather than any fundamental impossibility of understanding. For example, the exact mechanism by which supermassive black holes formed in the early universe is not known in complete detail, although several plausible mechanisms have been proposed and are being investigated through observations and simulations. Similarly, the precise nature of dark matter and dark energy remains unknown, although their properties can be characterized through their observable effects, and extensive research programs are underway to identify dark matter particles directly and to measure the properties of dark energy more accurately. The lack of complete understanding in these areas is acknowledged openly by scientists and motivates ongoing research efforts. The process of science involves proposing hypotheses, making predictions based on those hypotheses, testing the predictions through observation or experiment, and revising or rejecting hypotheses that do not match the data. This process is iterative and cumulative, with each generation of scientists building on the work of previous generations. and gradually refining and extending the body of scientific knowledge. In cosmology and astrophysics, progress often requires improvements in observational instruments, such as larger telescopes with greater light-collecting power, more sensitive detectors that can measure fainter signals, and space-based observatories that can observe wavelengths of light that do not penetrate Earth's atmosphere. Each new generation of instruments reveals new details and sometimes unexpected phenomena that require new theoretical explanations. And this cycle of observation and theory development continues to drive progress in understanding the universe. Current instruments and measurement techniques have certain limitations that constrain what can be observed and how accurately it can be measured. And these limitations arise from fundamental physical constraints, such as the diffraction of light, the quantum nature of light detection, and the finite size of telescopes, as well as from practical considerations, such as atmospheric turbulence, detector noise, and the availability of funding and technology. For example, ground-based optical telescopes are limited in resolution by the turbulence of Earth's atmosphere, which causes stars to twinkle and blurs the images of distant objects. Although this limitation can be partially overcome using adaptive optic systems that measure and correct for atmospheric distortions in real time, space-based telescopes avoid atmospheric effects entirely and can observe wavelengths of light that are absorbed by the atmosphere. But they are expensive to build and launch, and cannot be easily repaired or upgraded once in orbit. The cosmic microwave background radiation can be measured with extraordinary precision using specialized instruments on satellites and ground-based observatories. And these measurements have provided detailed information about the properties of the universe. But they are limited by foreground contamination from our own galaxy, by instrumental noise, and by the fundamental limit that the cosmic microwave background provides only a two-dimensional snapshot of the three-dimensional structure of the early universe. Observations of distant galaxies and supernovae can probe the expansion history of the universe and the distribution of matter, but they require accurate measurements of distance and redshift, which can be challenging for very faint or distant objects, and they can be affected by systematic errors, such as dust extinction, gravitational lensing, and uncertainties in the intrinsic properties of the objects being observed. Gravitational wave detectors, such as LIGO and Virgo, have opened a new window on the universe by detecting the ripples in spacetime produced by merging black holes and neutron stars. But these detectors are sensitive only to gravitational waves at certain frequencies and require extremely precise measurements to detect the tiny distortions of spacetime caused by passing gravitational waves. Future gravitational wave detectors, such as the space-based LISA mission, will be able to detect lower frequency gravitational waves from more massive black hole mergers and from other sources. And these observations will provide complementary information about the universe that is not accessible through electromagnetic observations. The development of new instruments and observational techniques is an ongoing process that requires collaboration between physicists, engineers, and astronomers. And each new capability brings the potential for new discoveries and deeper understanding. Scientific uncertainty exists in cosmology and other fields of science because measurements always have finite precision, because theoretical models involve approximations and assumptions, and because some phenomena are inherently probabilistic according to quantum mechanics. Uncertainty does not imply ignorance or lack of knowledge, but rather reflects a careful assessment of the reliability and precision of measurements and predictions. Scientists quantify uncertainty using statistical methods and report results with error bars or confidence intervals that indicate the range within which the true value is likely to lie. When different measurements of the same quantity give somewhat different results, scientists work to understand the sources of the discrepancy, which might include systematic errors in one or both measurements, unrecognized sources of noise or bias, or genuine variation in the quantity being measured. The Hubble tension mentioned earlier is an example of scientific uncertainty, where different methods of measuring the expansion rate of the universe give results that differ by more than the estimated uncertainties of the measurements. And this has prompted extensive investigation to determine whether one or both measurements have unrecognized errors, or whether the discrepancy reflects new physics that is not included in the standard cosmological model. This kind of tension between different measurements is a normal part of the scientific process and often leads to important insights and advances in understanding, either through the identification and correction of errors, or through the development of improved theoretical models that can explain the observations. The existence of uncertainty and disagreement does not undermine the validity of the scientific approach, but rather demonstrates the care with which scientists assess the reliability of their conclusions. The gradual acceptance of not knowing everything about the universe is an important aspect of the scientific worldview, which recognizes that knowledge is always provisional and subject to revision in light of new evidence. and that there will always be questions that have not yet been answered, and phenomena that have not yet been explained. This acceptance of uncertainty is not a weakness, but rather a strength of the scientific method, as it encourages continued investigation and prevents premature closure on questions that require more evidence to answer definitively. Scientists are trained to distinguish between what is known with high confidence based on extensive evidence, what is suspected but not yet confirmed, and what remains completely unknown. And this careful assessment of the state of knowledge is essential for making progress in research. In cosmology, there are many questions that remain open, such as what caused the initial expansion of the universe, whether the universe is finite or infinite in extent, what will be the ultimate fate of the universe in the far future, whether there are other universes beyond our own, and whether the laws of physics that apply in our observable universe are universal or could be different elsewhere. Some of these questions may be answerable through future observations and theoretical developments, while others may involve physics that is forever beyond the reach of direct observation. And scientists are careful to distinguish between questions that are empirically testable and those that are primarily speculative. The focus of cosmological research is on questions that can be addressed through observation and measurement, and on building theoretical frameworks that are consistent with all available evidence and that make testable predictions. The study of cosmic structure continues to reveal new details about the distribution and evolution of galaxies, the properties of dark matter and dark energy, and the processes that shaped the universe over billions of years. Large-scale surveys of galaxies, such as the Sloan Digital Sky Survey and its successors, have mapped the positions and properties of millions of galaxies and have measured the statistical properties of the galaxy distribution with unprecedented precision. These observations have been used to test cosmological models, to measure the expansion history of the universe, and to constrain the properties of dark energy and dark matter. Ongoing and future surveys will extend these measurements to larger volumes of space and to earlier times in cosmic history, providing even more detailed information about the evolution of cosmic structure. The intergalactic medium, which is the gas that fills the space between galaxies, also carries important information about cosmic history and the processes that have shaped the universe. This gas is mostly hydrogen and helium left over from the Big Bang. along with heavier elements produced in stars and dispersed into space through supernova explosions and galactic winds. Observations of distant quasars, which are extremely bright objects powered by supermassive black holes, allow astronomers to study the intergalactic medium by measuring how light from the quasar is absorbed as it passes through intervening gas clouds. The pattern of absorption lines in quasar spectra, known as the Lyman alpha forest, provides detailed information about the density, the temperature, and the chemical composition of the intergalactic medium at different times in cosmic history. And these observations have been used to study the reionization of the universe. When the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that filled the universe. During the Dark Ages, after recombination, the formation and evolution of structure in the universe is an ongoing process that continues today, with galaxies continuing to merge and grow, stars continuing to form and die, and the large-scale structure continuing to evolve. Under the influence of gravity and the expansion of space, the rate of star formation in the universe has declined significantly from its peak approximately 10 billion years ago. And as the universe continues to expand and age, the supply of gas available for star formation will continue to decline. And eventually, star formation will cease altogether when the available gas is exhausted. In the far future, assuming the current understanding of dark energy is correct, and the expansion of the universe continues to accelerate, galaxies outside our local group will move beyond our cosmic horizon, and the universe will become increasingly dark and empty. As stars burn out and black holes slowly evaporate through Hawking radiation over timescales of many trillions of years, the cosmic microwave background radiation will continue to cool as the universe expands, and its temperature will approach absolute zero in the distant future, and the wavelength of the radiation will be stretched to longer and longer wavelengths, eventually becoming undetectable. The large-scale structure of the universe will gradually fade as gravitational interactions between galaxies become less important, and as the accelerated expansion carries structures apart faster than gravity can pull them together. These predictions about the far future of the universe are based on extrapolating current observations and theoretical models forward in time over enormous timescales, and they are subject to considerable uncertainty because they depend on assumptions about the nature of dark energy and about whether the laws of physics remain constant over such long periods. Nevertheless, these extrapolations provide a scientifically grounded picture of how the universe might evolve over timescales far longer than the current age of the universe. The methods used in cosmology to study the universe rely heavily on careful measurement and statistical analysis of large data sets. And this work requires sophisticated instruments, extensive computational resources, and collaboration among researchers from many institutions and countries. Modern cosmology is a highly data-intensive field, with surveys producing terabytes or petabytes of data that must be processed, analyzed, and interpreted. And this work involves astronomers, physicists, statisticians, and computer scientists working together to extract meaningful results from the observations. The international nature of cosmological research reflects the fact that many questions about the universe can only be addressed through coordinated observations, using multiple facilities located around the world and in space, and through sharing of data and theoretical insights across national and institutional boundaries. The process of analyzing cosmological data involves many steps, including calibrating instruments to ensure accurate measurements, removing contaminating signals from the observations, modeling the expected signal based on theoretical predictions, comparing the observed signal with the model, and estimating the uncertainties in the results. Each of these steps requires careful attention to detail and thorough understanding of both the instruments and the physics being studied, and errors or oversights at any stage can lead to incorrect conclusions. The scientific community addresses this challenge through peer review, where research results are evaluated by other experts before publication, through replication of key results by independent groups using different methods or data sets, and through open sharing of data and analysis code that allows others to check and verify the work. This collective approach to research helps to ensure that conclusions are robust and that errors are identified and corrected. Theoretical work in cosmology involves developing mathematical models that describe cosmic phenomena, solving the equations that govern those models, and making predictions that can be compared with observations. This work ranges from analytical calculations that provide insight into basic principles to large-scale numerical simulations that model complex processes involving many interacting components. Computer simulations of structure formation, for example, track the motion of billions of particles, representing dark matter, and gas, as they evolve under the influence of gravity and other forces. And these simulations require powerful supercomputers and sophisticated algorithms to produce results in reasonable amounts of time. The output of these simulations can be compared with observations of the actual universe to test whether the underlying physical assumptions are correct, and to identify discrepancies that might point to new physics or to shortcomings in the model. The study of cosmic phenomena often requires combining information from many different sources and at many different wavelengths, as different types of observations provide complementary information about the same objects or processes. For example, studying a galaxy cluster might involve optical observations to identify and measure the positions and properties of individual galaxies. X-ray observations to study the hot gas that fills the space between galaxies. Radio observations to detect synchrotron emission from relativistic particles. And gravitational lensing measurements to map the distribution of total matter, including dark matter. Each type of observation is sensitive to different physical processes and provides different pieces of information. And combining all of these observations gives a more complete understanding of the cluster than any single observation could provide on its own. The interpretation of observations in cosmology often involves comparing measurements with predictions from theoretical models and using statistical methods to determine which models are most consistent with the data. This process, known as parameter estimation, involves adjusting the parameters of a model to find the values that best match the observations. And it also involves assessing how much uncertainty remains in the parameter values, given the precision of the measurements. In some cases, observations may be consistent with multiple different models or interpretations, and additional observations are needed to distinguish between the possibilities. The process of refining theoretical models and testing them against observations is ongoing and iterative, with each new generation of observations leading to improvements in the models and to new questions that motivate further observations. The cosmic web of structure that fills the universe consists of filaments and sheets of galaxies surrounding large voids, and this structure emerged naturally from the gravitational collapse of the small density fluctuations present in the early universe. The densest regions, where many filaments intersect, contain rich clusters of galaxies, with hundreds or thousands of member galaxies, while the filaments themselves contain smaller groups of galaxies and individual galaxies. The voids, which are regions of very low density, contain few or no galaxies, and make up the majority of the volume of the universe. The contrast between the dense regions and the voids has grown over time as matter has continued to flow from low-density regions toward high-density regions under the influence of gravity. And this process will continue in the future. Although the accelerating expansion of the universe will eventually halt the growth of structure on the largest scales, the formation of the first stars and galaxies in the universe during the period from a few 100 million years to about 1 billion years after the Big Bang is an area of active research, and observations with powerful telescopes such as the James Webb Space Telescope are providing new insights into this early epoch. The first stars are thought to have been very massive and very bright, and their radiation began the process of reionizing the neutral hydrogen that filled the universe after recombination. These stars also produced the first heavy elements through nuclear fusion and supernova explosions, enriching the intergalactic medium with metals that were incorporated into subsequent generations of stars, and that eventually made possible the formation of planets and life. The details of how the first stars formed, how massive they were, and how their radiation and supernova explosions affected their surroundings are topics of ongoing investigation that combine theoretical modeling with observations of the most distant galaxies that can be detected. Quasars, which are among the most luminous objects in the universe, are powered by supermassive black holes accreting matter at very high rates. And they were much more common in the past, when the universe was younger than they are today. Observations of quasars at high redshifts, corresponding to times when the universe was less than 1 billion years old, indicate that supermassive black holes with masses of billions of solar masses were already present at those early times. And this rapid formation and growth of black holes is not fully understood. Several mechanisms have been proposed to explain how such massive black holes could form so quickly, including the possibility that they grew from seed black holes formed by the collapse of the first stars, or that they formed directly from the collapse of massive gas clouds without going through a stellar phase, or that they grew through very rapid accretion in dense environments. Distinguishing between these possibilities requires detailed observations of high redshift quasars and their host galaxies, as well as theoretical modeling of black hole growth under different conditions. The chemical evolution of the universe, meaning the gradual enrichment of the intergalactic medium and of galaxies with heavier elements produced in stars, is an important aspect of cosmic history that affects the properties of subsequent generations of stars and the potential for planet formation. The very first stars formed from primordial gas, containing only hydrogen and helium, and they produced the first carbon, oxygen, iron, and other heavy elements through nuclear fusion in their cores. When these stars exploded as supernovae, they ejected these newly formed elements into the surrounding gas, enriching it and allowing the next generation of stars to form. With a small but non-zero abundance of heavy elements, over billions of years, successive generations of stars have continued to process gas through nuclear fusion and to return enriched material to the interstellar medium, gradually increasing the metallicity of the universe. The Sun and the solar system formed from gas that had already been enriched by many previous generations of stars. And the presence of heavy elements was essential for the formation of rocky planets like Earth, and for the chemistry that makes life possible. Star formation occurs in dense, molecular clouds within galaxies, where gas and dust are compressed by gravity, turbulence, shocks, and other processes, until they reach densities and temperatures high enough for gravitational collapse to occur. Once a region of a molecular cloud begins to collapse, it fragments into smaller clumps that continue to collapse independently, eventually forming individual stars or binary and multiple star systems. The process of star formation is regulated by feedback processes, including radiation pressure from newly formed stars, stellar winds, and supernova explosions, which can heat and disperse the surrounding gas and halt or slow the formation of new stars. Understanding the rate and efficiency of star formation in different environments and at different times in cosmic history is an important goal of astrophysical research, as star formation is the process by which gas is converted into stars, and ultimately into the heavy elements that enrich the universe. The life cycle of stars depends on their mass, with low-mass stars, like the Sun, living for billions of years and ending their lives relatively gently by ejecting their outer layers and leaving behind a white dwarf, while high-mass stars live for only millions of years and end their lives in powerful supernova explosions that can outshine entire galaxies for a brief period. These supernovae play a crucial role in the chemical evolution of the universe by producing and dispersing heavy elements, and they also play a role in regulating star formation by injecting energy into the interstellar medium and by compressing nearby gas clouds and triggering new episodes of star formation, the remnants of supernova explosions, which can be observed as expanding shells of hot gas, called supernova remnants, contain gas enriched with heavy elements, and can also contain neutron stars or black holes. Formed from the collapsed cores of the massive stars that exploded. Neutron stars are extremely dense objects, formed when the core of a massive star collapses during a supernova explosion and is compressed to densities comparable to the density of atomic nuclei. A neutron star with a mass similar to the Sun has a radius of only about 10 kilometers, and its surface gravity is so strong that a neutron star is about 1 billion times stronger than the gravity at Earth's surface. Neutron stars can be observed through various mechanisms, including pulsed radio emission if they are rotating rapidly and have strong magnetic fields, X-ray emission from hotspots on their surfaces or from matter accreting onto them, and gravitational wave emission if they are in binary systems that are gradually spiraling together. The detection of gravitational waves from merging neutron stars in 2017 provided confirmation of general relativity in the strong field regime, and also revealed that such mergers are a major site for the production of heavy elements through rapid neutron capture nucleosynthesis, a process that creates elements heavier than iron. The study of cosmic phenomena requires not only observations and theoretical modeling, but also careful consideration of the assumptions and limitations of both. Every observation involves some degree of selection bias, meaning that certain types of objects or phenomena are more likely to be detected than others. And accounting for these biases is essential for drawing correct conclusions from the data. Every theoretical model involves approximations and simplifications that are justified under certain conditions, but may break down in other regimes. And understanding the range of validity of a model is important for assessing the reliability of its predictions. The process of science involves constantly questioning assumptions, testing predictions against observations, and refining models to improve their accuracy and range of applicability. The future of cosmological research will be shaped by new observational facilities that are currently under construction or in the planning stages, including extremely large, ground-based telescopes, next-generation space telescopes, gravitational wave detectors, and neutrino observatories. These facilities will provide observations with unprecedented sensitivity and resolution, allowing astronomers to detect fainter and more distant objects, to study the universe at earlier times in cosmic history, and to test theoretical predictions with greater precision. The data from these facilities will require new analysis techniques and computational tools to process and interpret, and the results will undoubtedly lead to new discoveries and new questions about the universe. The pace of discovery in cosmology has accelerated dramatically over the past few decades, And there is every reason to expect that this pace will continue as new capabilities come online. As observations become more precise and theoretical models become more sophisticated, the boundaries of what is known about the universe continue to expand. But so do the boundaries of what is recognized as unknown or uncertain. Each new discovery reveals new questions and new areas for investigation. And the process of scientific inquiry is fundamentally open-ended, with no final endpoint where all questions have been answered. This open-ended nature of science is part of its strength, as it allows for continual refinement and improvement of understanding, and prevents dogmatism or premature closure on questions that require more evidence. The attitude of scientists toward the unknown is one of curiosity and patience, recognizing that some questions may take many years or even generations to answer, and that some questions may remain unanswered for the foreseeable future. The universe, as revealed by scientific observations and theoretical models, is an enormously complex and dynamic system that has evolved over billions of years through the action of physical processes that can be described mathematically and tested through observation. The success of this scientific approach in explaining phenomena, ranging from the motion of planets to the evolution of galaxies to the properties of elementary particles, demonstrates that the universe operates according to regular patterns that can be discovered and understood through systematic investigation. The fact that the same physical laws appear to apply everywhere in the observable universe and at all times for which observations are available suggests a deep underlying unity to nature. Even though many details remain to be worked out and many questions remain to be answered, the ongoing work of scientists around the world continues to refine and extend this understanding, adding new pieces to the puzzle, and occasionally requiring revisions to accommodate observations that do not fit previous expectations. The cosmic microwave background continues to cool as the universe expands, and its detailed properties continue to be measured with increasing precision by successive generations of instruments. Each new measurement provides slightly better constraints on cosmological parameters, and occasionally reveals unexpected features that require explanation. The large-scale distribution of galaxies continues to be mapped through surveys that observe millions of galaxies and measure their positions and properties. These surveys provide information about the expansion history of the universe, the growth of structure, and the properties of dark energy. Observations of distant supernovae continue to probe the expansion rate of the universe at different times in cosmic history, and these observations help to determine whether dark energy has remained constant over time or has evolved. Gravitational wave detections continue to reveal information about black holes and neutron stars, and about the merger history of these compact objects. Future detectors will extend the reach of gravitational wave astronomy to lower frequencies and more distant sources. The interplay between observation and theory in cosmology is a continuous process, with observations motivating new theoretical developments and theories making predictions that can be tested through new observations. When observations and theory disagree, scientists work to understand the source of the discrepancy, which might be due to errors or limitations in the observations, to oversimplifications or incorrect assumptions in the theory, or to genuine new physics that has not yet been incorporated into existing models. The resolution of such discrepancies often leads to important advances in understanding, and sometimes to paradigm shifts that fundamentally change how scientists think about the universe. The history of cosmology includes several such shifts, including the acceptance of the expanding universe model in the 1920s and 30s, the discovery of the cosmic microwave background radiation in the 1960s, and the discovery of the accelerating expansion in the late 1990s. Each of these shifts required revisions to previous ideas and opened new areas of investigation. The structure of the universe on the very largest scales appears to be approaching homogeneity, meaning that, when averaged over sufficiently large volumes, the properties of the universe become increasingly uniform. And this homogeneity is consistent with the assumption that underlies the standard cosmological model, which treats the universe as being homogeneous and isotropic on average. This assumption greatly simplifies the mathematical treatment of cosmic evolution and allows scientists to use relatively simple models to describe the overall behavior of the universe. Even though the universe is highly structured on smaller scales, the validity of this assumption has been tested through observations of the cosmic microwave background and through large-scale galaxy surveys. These observations confirm that the universe does indeed appear to be homogeneous when averaged over scales of hundreds of millions of light years or larger. The question of whether the universe is finite or infinite in extent is difficult to answer observationally, because observations can only probe the observable universe, which is necessarily finite due to the finite speed of light and the finite age of the universe. If the universe is infinite, then the observable universe is just an infinitesimal fraction of the total universe. And there are infinitely many regions that cannot be observed, because light from those regions has not yet had time to reach Earth. If the universe is finite, then it must have some overall geometry and topology, and different possible geometries have different observable consequences. Although distinguishing between these possibilities requires extremely precise measurements. Current observations are consistent with the universe being spatially flat, meaning that its geometry is Euclidean on large scales. A flat universe could be either finite or infinite in extent. So this question remains open. The concept of multiverses, or multiple universes, beyond our own observable universe, is a topic of theoretical speculation that arises in some versions of inflationary cosmology and in some interpretations of quantum mechanics. There is currently no empirical evidence for the existence of other universes, and it is not clear whether such evidence could ever be obtained. The scientific status of multiverse theories is debated within the physics community, with some researchers arguing that they represent legitimate extensions of well-established physics, and others arguing that they are untestable and therefore not properly scientific. This debate reflects deeper questions about the role of testability and empirical verification in science, and about how to evaluate theoretical ideas that make predictions about phenomena that may be inherently unobservable. For the purposes of observational cosmology, the focus remains on understanding the observable universe, using measurements that can actually be made. The properties of empty space, meaning space that contains no matter or radiation, are described by quantum field theory, which predicts that even empty space is filled with quantum fluctuations of various fields, and that these fluctuations have measurable effects. The Casimir effect, in which two conducting plates, placed very close together, experience an attractive force due to the modification of vacuum fluctuations between the plates, is one example of a measurable consequence of quantum fluctuations in empty space. The energy associated with these vacuum fluctuations is sometimes called vacuum energy or zero-point energy. According to quantum field theory, this energy should contribute to the energy density of the universe, and should therefore affect the expansion of the universe. However, calculations of the expected magnitude of this vacuum energy based on particle physics give a value that is vastly larger than the observed dark energy. Reconciling this discrepancy is one of the major, unsolved problems in theoretical physics. The constants of nature, such as the speed of light, the gravitational constant, and Planck's constant, appear to have the same values everywhere in the observable universe, and at all times for which measurements are available. The consistency of these constants is essential for the predictability and regularity of physical phenomena. If these constants varied from place to place or from time to time, the universe would be very different and might not support the formation of complex structures or the existence of life. Some theoretical ideas, such as certain versions of string theory, suggest that the constants of nature might have different values in different regions of a multiverse. But within our observable universe, there is no evidence for any variation in these constants. Searches for possible variations in fundamental constants over cosmic time have been conducted using observations of distant quasars and other objects. These searches have found no significant evidence for any changes, placing very tight constraints on how much the constants could have varied. The arrow of time, meaning the fact that physical processes have a preferred direction in time, and that the future is different from the past, is closely related to the second law of thermodynamics, which states that the entropy or disorder of a closed system tends to increase over time. The universe as a whole appears to have started in a very low entropy state at the time of the Big Bang, and it has been evolving toward higher entropy states ever since. This increase in entropy is what gives time its direction, and what distinguishes the past from the future. The question of why the universe started in such a low entropy state is not fully understood, and is related to the question of what caused or preceded the Big Bang. This remains an area of active theoretical research. Some cosmologists have proposed that the low entropy initial state might be a natural consequence of the laws of physics under certain conditions, while others have suggested that it might require special initial conditions or might be related to quantum effects in the very early universe. The study of the universe through scientific methods has revealed an enormously rich and complex picture that continues to evolve as new observations are made and new theoretical insights are developed. The universe is not static, but dynamic, with galaxies moving, stars forming and dying, black holes growing, and the overall expansion of space continuing and apparently accelerating. The processes that govern cosmic evolution operate over timescales ranging from fractions of a second for particle interactions to billions or trillions of years for the evolution of galaxies and the universe as a whole. Understanding these processes requires observations and theories that span this enormous range of scales. The success of cosmology in explaining observations and making predictions demonstrates that the universe operates according to understandable physical principles, even though many details remain to be discovered and many questions remain to be answered. The gradual accumulation of knowledge about the universe through careful observation and rigorous analysis continues to expand the boundaries of what is known, and this process shows no sign of reaching a final endpoint where all questions have been answered. Each generation of scientists builds on the work of previous generations, refining measurements, testing theories, and occasionally discovering entirely new phenomena that require new explanations. The attitude of scientists toward this ongoing process is one of curiosity, patience, and recognition that complete understanding may be an ideal, that is approached asymptotically rather than reached definitively. The willingness to acknowledge uncertainty, to revise or abandon ideas that are contradicted by evidence, and to follow the evidence wherever it leads, is fundamental to the scientific approach, and is what gives science its power to gradually improve understanding over time. The universe, as currently understood, is approximately 13.8 billion years old, contains hundreds of billions of galaxies, each containing billions to trillions of stars, is composed mostly of dark matter and dark energy, with ordinary matter making up only a small fraction of the total. It is expanding at an accelerating rate, and has evolved from a hot dense state through a sequence of phases that have produced the structures observed today. This understanding is based on multiple independent lines of evidence, including the cosmic microwave background radiation, the observed abundances of light elements, the large-scale structure of the universe, the expansion rate measured using distant supernovae, and many other observations. All of these observations fit together into a consistent picture, described by the lambda-CDM cosmological model. This model is successful in explaining a wide range of observations and in making predictions that have been confirmed by subsequent measurements. Although it also has some limitations and open questions that continue to motivate research. The nature of reality at the most fundamental level, including questions about why the universe exists, why it has the properties it does, and whether there is any ultimate explanation for the laws of physics, are questions that science approaches with caution, recognizing that they may lie beyond the reach of empirical investigation. Science focuses on describing how the universe behaves, rather than on explaining why it exists in the first place. This distinction is important for understanding both the power and the limitations of the scientific method. The regularities and patterns discovered through scientific investigation allow for predictions and explanations of observed phenomena, but they do not necessarily provide answers to every possible question that might be asked about the universe. The acceptance of these limitations is part of the scientific worldview, and does not diminish the value of the knowledge that has been gained through scientific research. The observable phenomena in the universe, from the motion of planets to the evolution of galaxies to the behavior of fundamental particles, can be described using mathematical equations and theoretical frameworks. These frameworks have been tested extensively through observation and experiment. These descriptions are not final or complete, but represent the current best understanding based on available evidence. They are subject to revision or refinement as new evidence becomes available. The process of science is characterized by this ongoing cycle of observation, hypothesis formation, prediction, testing, and revision. It is this process that has led to the current understanding of the universe, and that continues to drive progress in cosmology, and other scientific fields. The cumulative nature of scientific knowledge means that later discoveries build on earlier ones. Even when theories are revised or replaced, the observational facts that they were meant to explain remain valid and must be accounted for by any new theory. The expansion of space continues to carry galaxies away from each other. This expansion has no center and no edge within the observable universe. Every point in space is moving away from every other point. Observers in any galaxy would see all other galaxies moving away from them in a pattern that depends only on distance, with more distant galaxies receding faster. This pattern of expansion is exactly what is predicted by general relativity for a homogeneous and isotropic universe. And it has been confirmed by observations of galactic redshifts and distances over many decades. The expansion rate is characterized by the Hubble constant, which has been measured using various methods, with results that are generally consistent but show some tension between different approaches. Resolving this tension is an active area of current research and may require improved measurements or may indicate new physics that is not included in the standard cosmological model. The formation of structure in the universe, from small initial fluctuations through gravitational instability, is a process that has been studied extensively using both analytical theory and numerical simulations. The results of these studies have been compared with observations of the actual distribution of galaxies and of the temperature fluctuations in the cosmic microwave background. The agreement between simulations and observations provides strong support for the current understanding of structure formation and for the role of dark matter in this process. Simulations show that structure forms hierarchically, with small structures forming first and then merging to form larger structures. This hierarchical pattern is consistent with observations showing that massive galaxy clusters are rare and formed relatively recently in cosmic history, while smaller groups and individual galaxies are more common and formed earlier. The cosmic web structure that characterizes the distribution of galaxies on large scales is a natural outcome of gravitational instability acting on small initial density fluctuations. It arises because gravity tends to amplify differences in density, making dense regions denser and underdense regions more empty. The filamentary structure of the cosmic web reflects the anisotropic nature of gravitational collapse. Matter collapses first along one direction to form sheets, then along a second direction within the sheets to form filaments, while collapse along the third direction is slowest and leads to the formation of clusters at the intersections of filaments. This process has been studied in detail using simulations that follow the evolution of millions or billions of particles representing dark matter and gas. These simulations reproduce the observed large-scale structure of the universe with remarkable accuracy, lending strong support to the theoretical framework that describes structure formation. The distribution of matter in the universe continues to evolve. under the influence of gravity and the expansion of space. Structures on small scales continue to grow denser, while the expansion of space on large scales carries structures apart and eventually will prevent new structures from forming on the very largest scales. The balance between gravitational collapse and cosmic expansion depends on the density of matter and the properties of dark energy. Observations indicate that dark energy is currently dominant and is causing the expansion to accelerate. This means that the future evolution of structure will be different from the past evolution. Galaxy clusters that are not already gravitationally bound will never merge. The universe will become increasingly fragmented on large scales, with bound structures becoming increasingly isolated from each other. The end of this script approaches gradually with no clear conclusion. The processes described continue indefinitely into the future. Structures evolve slowly over billions of years. The expansion of space continues and perhaps accelerates. Stars form and die. Galaxies evolve. Black holes slowly accrete matter. Radiation continues to propagate through space. The temperature of the cosmic microwave background continues to decrease. The density of matter continues to decrease as space expands. The overall entropy of the universe continues to increase in accordance with the second law of thermodynamics. Far in the future, all available energy will have been converted into heat. All stars will have burned out. All black holes will have evaporated. All matter will decay into its most stable forms. The universe will consist of a nearly uniform distribution of extremely dilute radiation, at a temperature only infinitesimally above absolute zero, expanding forever into the future, with nothing changing except the continued expansion and cooling. This process proceeds without end, according to the current understanding, based on observations of dark energy and the acceleration of cosmic expansion. And now, as the cosmos stretches endlessly around you, as stars whisper their ancient light, as galaxies drift in the silent sea of space, there is nothing else, nothing left to chase, nothing to measure, nothing to understand. This is the moment to simply be, to feel the vastness, to rest within the mystery. For the universe has done its work, and all that remains is awe. May your mind float among the stars. May your heart feel the calm of cosmic silence. May you awaken with the wonder of new worlds. As the eternal dance of space and time continues. Good night.